right? And that's not true. Special relativity, that's not true. And that's not true. Okay, so it is true that space-time does have a geometry, but it's not Euclidean geometry. Okay? It turns out that this square is not this square plus this square, it's this square minus this square, and we'll get to that. So space-time does have a geometry, and that's an excellent point, but it's not the geometry we're familiar with. But we will discover what that geometry is upon the fair bit about. Okay, so one way that we can determine K is to make the assumption, Newton's assumption of universal time, or absolute time. Okay, by universal time, that means when 1 second elapses for Alice, then 1 second elapses for Bob. Okay, regardless of Bob's motion relative to Alice. Okay, so if that's the case, then what is the time for Bob? Ct plus d divided by c. Okay, so what we know then is that Ct plus d divided by c, that's the time for Alice here, and that's also the time for Bob, which we set equal to k times Ct, according to this picture here. So we're saying that that is equal to that. So on the right-hand side here we have kCt. K times Ct. Okay? So let's divide both sides. Let's take this c out here. So I'm sorry, remember taking this, we're taking the c out. Let's trace it. It's just k. Let me actually, let me just do this properly. So what we're saying is that d plus ct is equal to kCt. Okay, so now dividing both sides by c, what we get is solving for k. We get, let me actually write this thing. Here, just dividing both sides by c, we get this. Yeah. Okay, so this is equation number 2, we'll call it. Okay, so based upon this, so far this picture is just all common sense. Okay, so there's nothing fancy happening in this. We're just dealing with sound moving in air. Okay, and we have equation number 1 over here. So this is a simple equation. Equation number 2 here is based upon the assumption of an absolute or universal time. Okay, so now we have this equation, and this equation involves k and it also involves d. Okay, if you look at this equation, equation number 1, that involves p and c. And basically, we plug that equation into that equation, and we can solve for k. Okay, so the result is. I'll let you do the algebra there. So if I combine equations 1 and 2 and do a little bit of algebra, I find that k is equal to 1 over 1 minus d over c. Okay. And so we see that k indeed depends upon the velocity. There's a velocity. And in fact, it depends upon only the ratio of Bob's velocity relative to the speed of sound. Just the ratio of the dimensionless number d over c. Okay, so let's try to understand how this k is related to the Doppler shift. Something that it is, essentially the same thing. Okay, so let's try to make sense of that. So we will do another sort of thought experiment here. That's right. So if Bob goes to the speed of sound, then k goes to infinity. And if Bob exceeds the speed of sound, then k starts at minus infinity and then starts increasing again towards 0. Or to negative numbers. We will see that the Doppler shift is related to 1 over k. So, again, that's a very important point. Whenever you see any kind of formula or expression, look for places where weird things happen with that formula. So in that formula there, when d is equal to c, weird things happen. Okay? And it's important to understand what those mean. Okay, so here's the experiment in space. Okay, so here is Alice's x-axis. Okay, so space according to Alice. And Alice is at rest as usual in her space, and Bob, as usual, is moving in her space to the right of some ct. Now what we're going to do is we are going to allow Alice to send a sound signal, a tone. Okay, just like a siren from an ambulance or whatever. She's sending a tone, sending it over to Bob like this. Okay, so she's singing to Bob. Okay, so she's emitting this sound wave, which is moving with the speed c towards Bob. Okay, and these are successive crests of that sound wave. Okay, and those successive crests are being emitted with a certain frequency. Okay, so just put this down back here. Okay, so there's some frequency according to Alice. So Alice is saying that when I'm singing, and I'm sending out these sound waves at some frequency. The wave crests are coming out of my mouth at a certain rate. So many wave crests per second. So what is the time between the time on Alice's watch between those wave crests? If the frequency is fa, what is the time between those wave crests? over. Okay? So, let's go Alice's world line, which is this guy up here. Okay, so that's time. This is from C from this time away from Alice. And here is Bob. Bob is starts initially from this away from Alice, but he's moving this way. Okay, so that's Bob, so that's just like this. Okay? And so, we're going to look at the emission of two successive wave crests. The first one here is emitted and makes its way over to Bob at speed c. Okay, so here's the first wave crest emitted. It makes its way over to Bob at speed c, so it's 45 degrees, and then eventually catches up with Bob, and that wave crest walks over Bob. Okay, we'll look at the second wave crest, which is moving like this. The time elapsed between the emission of the first wave crest and the second wave crest, according to Alice, is TA, which is just 1 over frequency. Okay, that second wave crest now travels toward Bob, also 45 degrees, and it is Bob. Now the question is, what is the elapsed time for Bob here? What do you think? If the elapsed time here is TA for Alice, what's the elapsed time here for Bob? Yeah, K plus TA, right? So what that factor K does is it allows us to convert the elapsed times for Alice into elapsed times for Bob. So the original picture looked like this, where we had some CT over here, and then this becomes KCT. So basically, whatever is here, you multiply by K to get that part. Okay, so that'll be true also for if you take this interval multiplied by K to get that interval. Just like this interval multiplied by K to get that interval. Okay, so KT here is just going to be equal to K times TA. Okay, so let's see. So what does that tell us? So what's the frequency according to Bob? How is it related to T according to Bob? 1 over TD, which is 1 over K TA, which is 1 over K times 1 over TA is just FA. So in other words, the frequency with which Bob hears that tone coming from Alice will be related to the frequency that Alice measures by this factor, 1 over K. Okay, so 1 divided by K, there's our K, is 1 minus VOC. Okay, this is the usual Doppler shift. How many of you have studied the Doppler shift in your classes? Okay, so about half of you. So I want you to think about this. So what it's saying is, well, first of all, when V is 0, then the frequency according to Bob is the same as the frequency according to Alice, which is obvious. Alice is singing to Bob here, and Bob is at rest, and he hears the same frequency. But if Bob is drifting away from Alice, okay, then he's going to hear a lower tone. Okay, it's like that siren moving away. So the frequency is going to be lower. So as we increase D, 1 minus V over C is going to be a number less than 1. Okay, and the frequency according to Bob is going to decrease. He's going to hear a lower tone. What happens as V approaches C? What frequency according to Bob? When V is equal to C? 0. So when V is equal to C, we have 1 minus 1 is 0. So the frequency according to Bob is just 0. So if Bob is moving at the speed of sound away from Alice, then that whatever Alice says to her, says to him or sings to him, the frequency gets shifted all the way down to 0. And what if Bob exceeds the speed of sound? What if it's going to stay twice the speed of sound? What do we get? If V is twice the speed of sound? Yeah, so we get 1 minus 2 is negative 1. So we get the frequency according to Bob is negative the frequency according to Alice. What does that mean? Yeah. So basically Alice will say some stuff to Bob, oh Bob, I love you, while he's going away, right? And then that set of sound wave patterns is now in the air and moving like this at the speed of sound. Okay? If now Bob happens to be moving at faster than the speed of sound, he will see those sound waves go this way relative to him. And he will hear it in reverse. He will hear her talking backwards. What do you, I love you, when you say that backwards, what does that mean? You're going to get his speed right. Okay, so, what time are we at here? Oh, okay. Okay, so what I'd like to do is, maybe we can just take a break here because, and we'll do this tomorrow. It's already 10:30. Yeah. There's that if we observe the sound wave, you would see like the reverse of it, but the sound wave would never reach it. So, how would you hear it backwards? Okay, let's suppose that Alice has been, well, it depends. It depends on the fingers. Here's Alice, and she emits this chunk of sound. She starts talking yap, and she stops talking here. Okay, this chunk of sound is moving with this. And Bob is behind. Okay, so I'm just saying that let's suppose that Bob is such that, supposed to be moving at the speed of sound. And so, and he's at a certain distance from her, so that he's sitting here. So that chunk of sound is moving like this, and he's sitting right in the middle of it. Okay, then if he moves to the right, if he moves to the left like this, then he's moving at less than the speed of sound, and you will hear just lower frequency, but it's the correct way forward. If he's moving fast at the speed of sound, he'll be moving relative to that clump of sound, he'll be moving to the right. So let's imagine that Alice has, in fact, said this repeatedly over and over and over again before. And so her sound waves still all the space and repeat pattern of sound. And then you can move either forward or backwards based on the left speed sound. She'll say in the middle of the sound, nothing was set to it, and she's using an exactly the sound. So thing is that the frequency is 0, right? So if you still hear something, if we hear nothing sounds. So yeah, we've got this wave, and sort of this wave is moving to GC, the Bob has caught up with it, and so he's just sitting there, the Bob is just sitting there around, and there's this pressure wave around him to take this pressure. So he's in a region with slightly higher pressure than average, and it's just static. If I were to take like, a box, stick it over your head, pressurize the box a bit, hold it there. You're on hearing it, right? Yeah. And then if I, and then if he moves slowly from here to here, and now moves out to see the sound, you're like having, you'll feel like a lower pressure, you'll be like having pull on the box a bit. And so, you're just holding it out, but yeah, it's zero rate, you're going to go on the vibrator. Yeah, but let's imagine that sound, Alice has been reacting for a long time. And the sound fills, from this point all the way forward, sound waves fill the entire space. And then Bob comes along. Again. And let's see, so I want to recap what we did yesterday. So yesterday we did a very simple experiment. We had Alice at rest in still air, and we had Bob moving past her like this. And remember, as soon as Bob moves past her, she starts her watch going. She waits for a certain time T. She claps her hands. The sound signal goes chasing after Bob, and it reaches Bob, and then Bob claps his hands, sends the sound signal back to Alice. And we came up with this picture here. So here is Alice. Alice is at rest with respect to the air. Okay, and so her world line is just vertical like that. Okay, and remember, we're plotting the speed of sound c times time for Alice. And what's Bob doing? Well, Bob is drifting across her frame as time goes on. So his world line, he crosses her path over here. His world line goes up like this. So this is Bob's time axis. His clock is ticking. Tick 1, 2, 3, 4, 5 on his clock. Okay, as he's floating across her space. And just as a reference here, 45 degrees. What's it 45 degrees? So if Alice were to clap her hands at the same time that Bob passed her location, then this sound wave would travel faster than Bob and would go no further than him in a given time. Okay, so this is a sound wave. So this is 45 degrees. And here's C is the speed of sound. Okay, so we got that. And then as soon as Bob crosses her path, she starts her stopwatch and she waits a certain time, capital T, on her clock, and then she emits the sound wave. She claps her hands. So because we're plotting C times T, we put CT here. Okay, and then that sound signal goes out at 45 degrees, like this. It catches up with Bob, and he claps his hands, and he sends the sound signal back like that. And the important thing here is that this is 45 degrees, obviously because Alice is at rest with respect to the air, and any sound that she emits, she's going to observe it to be moving at the speed of sound. But this one here is also at 45 degrees. This is the important one. This is also at 45 degrees, even though Bob is a moving source. Bob is drifting with respect to the air. He claps his hands, but as soon as he claps his hands, he sends up a disturbance in still air. Also, we put a couple other things in the picture. We labeled the Bob's velocity, v. He's drifting with speed v to the right. And we suppose that at the instant Bob receives her sound signal, the instant he hears Alice's clap, we suppose that he has traveled that distance d in Alice's space. So he started at Alice's location, and he drifts. When he hears the clap, he's a distance d away from Alice. Okay, and then the beautiful thing about plotting CT versus S, instead of T versus X, these are 45s. And so if that's D, then what's that? And there's also D. It's not sure what this is. CT. It's not right there. Okay, so that's our picture there. And from that picture, what we did is, there was subliminal subsonic. Okay, so Bob is moving at subsonic speed, so slower than the speed of sound. Okay, so that's that. And the most important thing on this picture is this time here. Okay, so we're wondering how much time it elapsed for Bob. Okay, so what we do know is that time must be proportional to CT. So we talked about that as well. So if this, so we said it was K times CT. That's the number of tick marks on here representing the ticking of Bob's clock. Okay, and the reason for that is remember, if we were to double this time, say make it this big, then we would also double this time. Okay, so whatever this time is, that's our unknown. It must be just proportional to that time over there. Okay, so that diagram there makes no assumptions whatsoever. Okay, it's super basic physics. It's just Alice at rest in air, Bob drifting through, and everything. Very, very simple physics. Okay, so, and then what we did is, we said, okay, well, let's try to figure out what this K is, because that's the really important thing. If we know what that K is, then we know how much time elapses for Bob, when a certain amount of time elapses for Alice. One way to determine K is to simply assume. Simply assume that when 1 second elapses for Alice, 1 second elapses for Bob, and 1 second elapses for everyone in the universe, there's such a thing as absolute or universal time. And 1 second elapses for one person, 1 second elapses for anyone, regardless of their state of motion. In which case, we just said, oh, well, that means that this time here, D plus CT must equal that, KCT, and then we solved for K. And then we found that, in fact, K is just the ordinary Doppler shift for sound in air. Okay? And then what we're going to do now is we're going to drop that assumption about universal time and find a different way of calculating K, a more natural way of calculating K. And we'll find that K is not what we got before, something different. And it tells us that the amount of time elapsed for Bob from here to here is not the same as the amount of time elapsed for Alice from here to here. Universal time does not exist. Okay? And time is different for everybody. Everybody has their own sense of time. Okay, so that's the goal here. Okay, so to reach that goal, what we're going to do is we're going to take this picture here, which works for sound in air, and we're going to imagine that instead of Alice and Bob exchanging sound signals in air at rest, we're going to imagine that they're exchanging light signals. Okay, so the speed of sound is going to become the speed of light, and subsonic is going to become subluminal and all that stuff. So we're just replacing sound with light. Okay, so the first step here is just so that we have a concrete picture of what's going on, and to make the picture as close as possible to what we had for sound, what we're going to do is we're going to imagine that light is a wave in ether. So how many of you know about the concept of ether, heard about the concept of it? How many of you not heard ether before, the word ether? Okay, so about a third of you. Okay, so it turns out that in the early 1800s, there were experiments done which showed that light is a wave phenomenon. Okay, and so it exhibits wave properties like diffraction, interference, that kind of stuff. So everyone thought, yeah, okay, light is a wave. Great, fantastic. Okay, so then they looked at other waves. They looked at water waves, and they noticed, what is a water wave? A water wave is a disturbance of some medium. Okay, so the water molecules, when you splash in the water, the water molecules are going up and down like this. Okay, so there's something waving. In the case of water waves, it's the water molecules that are waving. Okay, they also knew that sound is just vibrations of some other medium, air. Okay, so when you talk and sound comes out, it just means that air molecules are vibrating up and down. Okay, so the air molecules are waving back and forth. So then they thought, well, okay, light is a wave. So what's waving? Okay, and they thought, what's waving? Well, I don't know. Can't really see anything waving. Okay, and so they invented this medium called the ether. And they imagined that the ether is the sort of elastic medium, like air or like water, that pervades all of the universe, fills all of space. And that light is just a wave in this ether. So when I click on a flashlight, what it does is, imagine this ether as like jelly. Okay, full of jelly filling the whole universe. If I jiggle the jelly over here, then it will jiggle neighboring jelly, it will jiggle neighboring jelly, and so on, like dominoes to get a wave going out. So they imagine that light is a waving of this sort of elastic medium they call the ether. Okay, so let's go with that model of light. Okay, because that model of light was actually what was used for all of the 1800s until the beginning of the 1900s. Okay, so let's suppose that light is a wave in ether for a moment. I'll put a question mark there, okay, because it actually will show that it's not that. So light is a wave in ether, and that's exactly analogous to sound being a wave in air. Okay, so what we're doing is we're going to take this picture here, and in the backdrop of this picture, we have in mind still air. So now in the backdrop of this picture, we're going to have in mind ether. Okay, and Alice does rest with respect to this mysterious medium called the ether. And she is, instead of clapping her hands and sending a sound signal, she's sending light signals. The point is that this situation here, light as a wave in ether, is completely analogous, 100% the same as sound as a wave in air. So we can take this diagram and use exactly the same thing, draw exactly the same picture for an experiment in which Bob is drifting through her frame, Alice waits on key, clicks on her laser, and sends that laser light over here, and Bob has a mirror which reflects that laser like that. And the important thing is, when he reflects it back, the speed of light is infinite with the motion of the source. So in this case, Bob is drifting through that mysterious ether medium, but when he clicks on his flashlight or laser or sends it back to the mirror, that light travels with respect to the still ether with the speed c, which is now the speed of light. And so Alice will measure that speed to be c independent of the motion of Bob, depending on how fast he's moving under a layer toward her. So this becomes c becomes the speed of light, and this becomes Bob is moving subsonic but subluminal. And something moving superluminal would be like that. That's the speed of light. Okay, so that's our picture, which is carried over in its entirety without any change. Okay, so Einstein, let's now switch to a little bit about Einstein and the theory of special relativity. So Einstein based his theory of special relativity on two principles, and one of those principles has to do with the speed of light. Anyone tell me what that principle states? Yeah. Say that speed of light, the speed of light is the same relative to speed of light. Okay. Yeah, so the speed of light is the same relative to so that's the general consensus of what Einstein said, is that somehow the speed of light is the universal constant, the same for everybody, the same in any reference frame, the same, blah, blah, blah. That's actually not what Einstein said. Okay, so this is a very important point that I want to make here. What Einstein actually said was this. Okay, so there are two principles, principle 1 and 2. We'll start with principle 2, which is the speed of light principle. Okay, so understanding this principle properly will really help you understand the logic of special relativity, why it makes sense, why it's totally believable, why it's the most natural thing you can imagine, or the most natural way the universe could be. Okay, so let me actually read what Einstein said. And before I read that, I have to, before I read the principle, I need to read what he said a little bit earlier, some terminology. Okay, so this is from his 1905 paper on special relativity. He says, well, let us take a system of coordinates in which the equations of Newtonian mechanics hold good. In order to render our presentation more precise and to distinguish this system of coordinates verbally from others, which will be introduced hereafter, we call it the stationary system. Okay, so what he's introducing is a reference frame, a coordinate system. Okay, so Alice is some state of motion. Okay,